Hello, everyone. Welcome to our lecture on polar bonds and molecules. Um, Polar bonds only refer to covalent bonds. So just for clarity, we're not talking about ionic bonds, those plus and minus charges that you find um, between ions. These are polar bonds are a certain subtype of covalent bonds. And so let's talk a little bit about polar and nonpolar covalent bonds. So a covalent bond is made up of a pair or more of electrons that are shared between two nonmetals. And this bonding pair of electrons is kind of tugged back and forth between the two atoms that share those electrons. If those two atoms are able to share the electrons evenly, the bonding if the bonding electrons are shared evenly, then you have a nonpolar covalent bond. In other words, um, there's not any uneven distribution of the electrons between the two atoms. They share evenly between the electrons are shared evenly between the two atoms. Examples of this are, for example, diatomic oxygen. Diatomic means two, so diatomic oxygen is just O2, the stuff we breathe. Another example is nitrogen, N2, or chlorine, Cl2. In each of these examples, you'll notice the molecule we're talking about is made up of two atoms of the same type, two oxygens, or two nitrogens, or two chlorines. And so in that case, the covalent bond that forms between the two of them is completely evenly shared because it's an identical atom on either side. And that's kind of what we're trying to show here with this little picture. Hydrogen, of course, is another example of a hydrogen gas, H2, of a nonpolar covalent bond. The electron pair that is shared between the two of them is shared equally. Neither hydrogen atom in this compound is able to pull more strongly on the electron pair than the other atom is. If, on the other hand, the covalent bond that joins the two atoms is not shared evenly, that can happen when the two atoms are of different elements, like here where we have chlorine and hydrogen in a covalent bond together. So there's a single electron pair being shared between chlorine and hydrogen. But chlorine is quite electronegative compared to hydrogen. So chlorine likes to have electrons near it, and it's going to pull the shared bonding pair of electrons towards chlorine. All right, and that means it's going to be pulled away from hydrogen. So in other words, this bonding pair that make up the covalent bond is unevenly shared. And that is a, where's my mouse? That is a polar covalent bond. So even sharing, nonpolar. Uneven sharing, polar. That's the difference. So that was an example with HCl, hydrochloric acid. Another example is with water. So it doesn't have to just be two atoms involved. Water is one oxygen and two hydrogens. And there are a couple of representations of water down here. Oxygen has a single pair, sharing a single pair of electrons with one hydrogen and another single pair of electrons with another hydrogen. But remember that oxygen is also pretty electronegative, so it's going to want to pull electrons towards itself. That's what electronegative means. So that means that this electron pair that's being shared here and here, these are not evenly shared. Oxygen gets a bigger share of the bond than the hydrogens do. All right, and so oxygen or water is another example of a polar covalent bond. Now we can show this polarity, we can refer to polarity using the Greek letter delta. That's this symbol right here. It's called delta. And if we use a plus symbol with the delta, delta plus means a small partial positive charge. I'm going to get to what that means in a second. Delta minus means a small partial negative charge. And so here in this representation of water, we have a delta minus written near the oxygen and a delta plus written near each hydrogen. That's a way of indicating that the bonds in this molecule are polar. They are unevenly shared between the constituent atoms. And oxygen, by pulling those electron pairs closer to itself, actually develops a small partial negative charge. because it has electrons that are closer to it. So it's a little bit negative, not a full charge, not a full -1 charge, just a partial charge. Similarly, the two hydrogens each has a small positive charge associated with it, because the electron pairs are being pulled away from hydrogen, and that leaves a small positive charge on each hydrogen. And of course, this whole entire molecule is still neutral, so these two small positive charges are balanced by this small negative charge. Does that make sense? This balances out these two. The whole entire molecule is neutral, but there's an uneven charge distribution in the molecule. And any molecule that has two, we would call these poles. Here's a positive pole and here's a negative pole. We call this a dipole. And that's where the word polar comes from when we're talking about polar covalent bonds. All right, so that's what we need to know about polar versus nonpolar covalent bonds. It really comes down to what our atoms make up the bond and how closely related are they, or how close are they to each other on the periodic table, how similar is their electronegativity. There are other kinds of attractions between molecules. We've actually been talking about attractions within a molecule, something that holds an ionic or a covalent compound together, but there are also interactions between molecules. These are called VanDer Waals forces. These are between molecules, not within a molecule. They're different from ionic or covalent bonds because ionic and covalent bonds hold together molecules. Now we're talking about something that holds one molecule towards another, pulls one molecule towards another. So the types of VanDer Waals forces are hydrogen bonds, dispersion forces, and dipole-dipole interactions. These are much weaker than ionic or covalent bonds. Okay, so the dipole interaction is the electrostatic interaction that occurs between oppositely charged regions. So if you think about that polar molecule again that we saw a couple slides back, where there was a small negative charge and a small positive charge on different ends of the water molecule, those positively charged regions can attract nearby negatively charged regions. So it's an electrostatic interaction, kind of like what you see with an ionic bond, but it's much weaker and it's between molecules, not within a formula unit or a molecule. Hydrogen bonds are another form or another example of a VanDer Waals force. These are weak bonds that form between the molecules of water. They're even weaker than dipole interactions. And my example here is the same example we've had already. When hydrogen bonds to a very electronegative element like fluorine, the electron from hydrogen is pulled strongly towards fluorine, which produces a slight positive charge on the hydrogen and a slight negative charge on the fluorine. This is a polar covalent bond between hydrogen and fluorine, and it's that resulting positives and negatives are able to interact with other nearby molecules to hold the substance together. The last type of force we need to talk about is a dispersion force. This is the attraction between any two molecules. They don't have to be polar covalent bonds. These are just due to the random movements of electrons in a molecule. So electrons are not static, they move around all the time, and at any random moment, it's possible that most of the electrons in a molecule will be in one place, just randomly, as opposed to dispersed evenly all over the molecule. So if you've got all the electrons piling up on one side of, for example, a hydrogen gas, H2 molecule, if by chance all the electrons end up over on near one of the hydrogen atoms at a given moment, you will produce a small temporary dipole, a small positive charge on one hydrogen and a small negative charge on the other. That's a dipole, and that's what we would call a dispersion force. This is weaker than either of the other two forces we talked about, but they apply to all molecules, so there's just piles and piles of this kind of interaction that happen, and this helps to hold matter together, hold one molecule to another. So that's the three types of VanDer Waals forces that you need to know about. And that's it for now.